Welcome back everyone. This session is week 2 and we will be covering the topic which would be related to lithium-ion cell-to-cell interconnections, thermal load calculations and IP design. Just to recap on what we did last week. So in the previous week session where we concentrated on lithium-ion cell chemistries, different form factors, the main differences between them, advantages and disadvantages. When it comes to lithium-ion cell chemistry, how are the voltages differing for each chemistry, and what are the constructions of the cell, what are the advantages and disadvantages. And we also had topics which are related to cell to module to pack conversion, what are the different form factors, what are all the parts that are needed in a module for cylindrical cell, pouch cell, etc. And we went through a case study based on how a cell has to be selected, different form factors, several factors like C rates, life cycles, SOC percent, and that means the voltage cutoff, dimensions of cells, temperature limits, etc. And how a cell block has to be assembled considering a thermal foam, HCP, etc. So there was also a session where we understood the cell arrangement has to be happen in a series and parallel combination in a module, and how are they configured in a module, and how are the modules translated into a pack, what are the volume needs for cell, electronic components and other components. So we also had what are the different components available and what are the role of those components in the whole battery pack, which could be electrical, mechanical, electronics, etc. And we also had a topic which we were discussing on the power cable requirement and the selection of right power cables. So in brief, those were the topics which we had in the last week. And in this week, this is the table of contents where we have sessions mostly focusing on what are the different types of cell interconnections, what is the need of a weld joint, its advantages and disadvantages related to each process of welding, and we have a comparison between those technologies. This session would also be focused on various important topics like battery pack design, which is thermal loop design, thermal interface material considerations, which will also involve, this session will also involve the Ingress protection classifications, type of sealings needed for the battery pack, etc. Learning objectives. So as explained in our content slide, we would study mostly on the materials used for the busbar, cell-to-cell interconnections, which material is best and why having a proper material gives us advantages, and how and what are the effects of bad welding or a poor welding, and what is the performance on the battery pack. We'll also discuss on those principles involved in brief. And then we'll have a good session, amount of session concentrating on the thermal part designs, which include the SOC percent based findings, how the heat is generated at different SOC, a little bit of mathematical expressions using law of conduction, and understand the temperature rise in the cell. What are the certain guidelines that we need to be followed while we design a good ingress protection pack or a gasket design. So we'll look on how to do that, and an overview of different types of sealings that are used in the battery pack. So this would be the objectives of this session, and now quickly let us go into the session where we'll start with the different types of cell interconnections. So in this section, firstly we'll go through different welding methods that could be used in lithium-ion cells and their working principle in brief. So let us start when we say like most widely used welding techniques are for joining one cell to another cell using a busbar. So that is how the cells are interconnected using a busbar, and these welding connections can be done through different technologies. And as lithium-ion cell exists in different form factors, which makes the construction and the casing or the enclosure different materials, a certain welding could not be used for a few of them. So different welding techniques are used for different cells, and one cannot be commonized for everyone. So in this process, let us start with cylindrical cells, which is most widely used. Cylindrical cells, and these cylindrical cells are mostly welded by using a technique of spot welding or a wire bonding, but spot welding is very much common throughout the world, and wire bonding is the one which has been lately come into consideration, but it is a little bit costly, but it is good, it is effective. So, and whereas when we go with the prismatic and pouch cells, these are connected through a common approach, which is laser welding, which is common for both. And then whereas pouch cells only have a unique welding method called as ultrasonic welding, which could be used only for pouch cells. And we have also seen how pouch cells would look like the copper tab which it has, the aluminum tab which it has, the thickness of those tabs are very less. So that means the same spot welding could also be used for the spot cells, because the tabs of those end terminals or the positive and negative terminals are very thin. We could also use spot welding, but how to angle of weld and the way the probes are, that makes a little bit difficult, but still if the jigs and fixtures are designed well, it could be managed. Whereas with the prismatic cells, apart from the laser welding, we have manual cell to cell interconnections also, which could be done through nut and bolt. So this is used in several EVs, by the way, whereas it eliminates a lot of process cost, eliminating high equipment investments, etc. This also seems simple, as the process is just to tighten a bus bar, place a bus bar, use a bolt or a nut and tighten it. But this type of cell connections has its own disadvantages, like as we talked in the last session, like this can have high contact resistance, and there could also be high chances of bus bar loosening up due to heavy vibrations and mechanical shocks, etc. And therefore having a good joint between a cell to cell through a bus bar is really important, and therefore it has to be torque tightened. But how much can a torque sustain that vibration is something up to a question of a real time scenario. So it is something which has to be evaluated again and again, or it will also need a maintenance thing, that after a certain number of months or days, the nuts and bolts have to be tightened again and again. So that is something which has to be followed for certain limitations. So if there are certain limitations in welding, there has to be some answers to that. So these are the different types of cell-to-cell interconnections. Then we'll go to the next topic, which is, this is one of those slides. In the earlier slide we see the spot welding. So we have nickel strips, we have cylindrical cells, and they are welded with each other with a probe, which is for spot welding the cells and the bus bars. And the next one is the wire bonding. So we have a bus bar, and we have cylindrical cells, and we have small wires bonding the bus bar and the cylindrical cell. So these are the two techniques for cylindrical cell. And then we have prismatic cell laser welding. So this is a bus bar, and we have placed the bus bar on the top. So remember, prismatic cell can have laser welding, or it could be done through nut and bolt. But here the best one is always the laser welding, but it comes for a cost. So over here, this is a cell which is having a bus bar, and it is welded to the tab of this bus bar, where the fusion happens by melting of the materials to the heat generated. So over here we see everything, all the cells are connected through bus bar, positive, negative, positive, negative, positive, negative, all connected through bus bar. So this is one of the fusion of how bus bars is. So here one thing what we could see here in the prismatic bus bar, how the cell is welded, there is a bare tab which is the unwelded portion. So the construction of the tab is decided that which kind of cell to cell joining is used. So this starts from the cell construction. So if you want to have a tab, for example, if this tab is designed to have a laser welding connection only. If you want to have a tab with a screw and a nut or a bolt, that has to be mentioned to the cell manufacturer, or you need to pick up a cell which is having that kind of construction. So there are different kinds of constructions that a tab can be made, so that has to be conveyed properly if you are looking for a special cell which is made for you. And in fact, you can also make your tab customized according to your application, so that you can use the same technique of cell to cell interconnection joining. But there are again some disadvantages, as we spoke on regarding the nut and bolt one. Laser welding has certain advantages, that when there is a proper fusion, the current losses are not there, because there's a good contact found between them, and the resistance while passing the current is less. So what is the importance of right welding joint? So before we go and understand welding process, bus bar, cell, etc., it's important to understand what is the right welding joint, how it has to be rightly done, and what are the impacts of poor welding joint. So just to understand what is the importance of right welding joint, now we know what a cell is, what a cell to bus bar connection is and all. So the only way to join them is welding. Usually if we go with the mechanical terminology, welding is something when you join two different parts or metals together, and over there the strength is the only thing which plays a major role. Whereas when it comes to lithium ion cell, we have cell to cell interconnection with a bus bar used for welding both the cells together. And when that is done, yes, strength is definitely a major concern. It has to be there, strength has to be good, but there is an additional feature which comes up, which is functionality. This additional functionality is the right word, which is the current also has to pass through it without much of a resistance added to that. So which is the most important part for lithium ion cell to cell busbar welding. So if that is not taken into picture, I think there will be huge resistance add up because of the poor welding joint, and all the current which is passed is going to be emitted out as heat at the busbar joints. So this is how it is important to know that along with the strength, the right joint has to be made, which it should be very good enough to conduct all the electricity. It should limit as much as possible hotspots formation on the cell to cell interconnects with the busbar. So before that we choose the right cell to cell design considerations, we need to also understand what is the type of application that this battery pack is going to, and what is the type of C rate that the battery pack is going to witness, so expect to deliver, or the bus bar is going to witness. Because why application is, we also need to understand what is the environment the battery pack is subjected to, and what is the strength the weld joint is required to handle. If it's going to be earth moving equipment or a tractor or any such applications, there will be huge vibrations constantly adding on the bus bars, and it should be very important to assess those kind of vibrations when we make a right welding joint, so that the time and the area of weld joint which we are going to make is decided depending on those kind of applications which we choose. And then what is the C rate of the bus battery pack? Because bus battery pack or a car battery pack or a high voltage battery pack or any battery pack, the C rates that it would deliver matters the most. If you make a battery pack of a high voltage battery pack which is delivering 1C or 2C current, and you have made a bus bar joint which is only capable of taking up to 0.5C or 0.75C, when you withdraw 1C or 2C current, the bus bar joint is going to be generally heated up. One, you would design a wrong bus bar. Two, the area for the joining of the bus bar would be less, and because of that your bus bar would constantly at a higher temperature, and because of that higher temperature there are high chances that the joint between the two metals would slowly break. So that is the reason you should also consider the C rate for the bus bar when you join. And then the most important, what is the type of material that you are going to use for the bus bar to join. Your material used should have good thermal conductivity, it should have good electrical conductivity, it should be weighing less. There are a lot of factors that would come in when you choose the material bus bar, and also the structural integrity of the module. All these are the factors that would creep in, make the right weld joint. If there is a bad cell to cell interconnections, definitely these are the following factors which would happen. Like there would be high resistance near the surface and the bus bar tab. The joints would always be overheated, and you will have to withstand high vibration loads, and that would definitely not happen because your joints are always overheated. That's a weak bond, and your bond can break at any point of time due to high vibrations. So I would recommend you to go through this link which is pasted below, which is from a very good OEM who makes all the welding technology machines, which would give you an understanding of how C rates and how the vibration loads, etc., that the bus bar and the cell bond goes through when it is welded, and what a bad cell design would lead to, how the contact resistance of this bus bar makes a major impact on the battery pack performance, etc. This is a good article which you could go through to the internet at a later point of time. So now let us go to the next topic, which is busbar welding the cell. So let us understand in this sessions like what is the type of busbar and cell welding technique and principle behind it, and the materials used for the busbar. So the first one is cylindrical cell to cell interconnections. So you know, cylindrical cell to cell interconnections, the spot welding is the most common one, which is widely used throughout for any of the cell. This commonization of this cylindrical cell has gone to such extent that you can readily get a catalog for cylindrical cells, what kind of bus bar it is used. So all these are commonized mostly. But what is not commonized is the process of welding. So each OEM has its own set of traditional procedures to arrive at the right welding parameters. So over here you see a machine which is a spot welding machine, and you have a jig, you have cells with bus bars, and these are the probes. needed for welding the cell with the bus bars. So how is it done is this machine sends a short high current pulse which is passed through the two metals, and that helps in bonding the bus bar and the cells together. So that is how a bond is formed between bus bar and the cells. So this is for a very short period of time, and this spot welding technique happens real fast and real quickly. So that's the reason it has been majorly adopted by most of the people using cylindrical cells. So that is a great advantage which this has. So this process can be automated, this process can be manual also. This is what spot welding technique is, and mostly the bus bars used in the spot welding, that is for the cylindrical cells, is the nickel bus bars, or they could either be copper bus bars plated with nickel. Most of them are this one. So usually copper is coated, copper is used with nickel on them, so that there is a good conductivity, so that the heat generated is dissipated as fast as possible. These nickel bus bars are available in straight orientation bus bars or zigzag bus bars. So over here we can see we have straight ladder kind of bus bars. These are called ladder nickel bus bars, and these are called zigzag bus bars because ladder in the sense because of their look, how they look like. These are bus bars used for any positive and negative combinations. So irrespective of the positive side or the negative side of the cell, the bus bar can be placed and straightly welded. This the positive and the negative tabs do not have any effect on this bus bar. Both can be welded as equal as possible, and both can have a good strength. But one thing over here, which would be as a battery engineer or a battery pack manufacturer or a battery enthusiastic, which you would like to explore is, this machine has a display unit and it has a parameter values over here. So this is where you need to work out. Like on the day one, you would never get a good joint. You will have to test at different parameters. You need to evaluate different parameters for the bus bar, or like it could be different thing, like at what current you would pass, what is the welding time that you want to do, etc. So there is a good amount of trial and error that you need to do to achieve the right welding parameters for the cell and the bus bar to join together. So what are those? That we will find out in the next slide, which is the spot welding parameters. So some of the spot welding parameters which play a vital role are the maximum welding current, and then you have pressing force, and you have electrode diameter. So these are something which are important. So even though you have all the bus bars, you have all the cells available, you have all the cell holders available and all, it's the whole process of welding will be very important in welding. So you'll have to evolve those technologies over a period of time. You cannot get that right. You'll have to do a lot of iterations while doing that. So when we see, we'll just talk a little bit about the nickel strip. So basically we have a nickel strip which would be of 0.15 mm to 0.3 mm, and we have slots at regular intervals, and then we have a welding electrode which is placed on the tip on either side of the slot, and because it's a nickel ribbon, it has a slot. The current is forced to travel through the cell, which is the shorter distance for the current to travel. And this can provide a solid weld with less energy and less heat. Question can arise, does spot welding without slot work? Yes. But when that is being done, a large percentage of current passes through nickel strip from one welding probe to other. So which means a large percent of current also leads to large current and large heat being generated. So which would also mean that the amount of nickel required to weld would be enough so that a good joint can form. But it will be a lot more hotter than melting a solder material. Like the temperature can go up to 1455 degrees centigrade. So just to avoid that, just to avoid such kind of high temperatures, so why is such high need? So you can always make a slot. You can create a current path by passing the current through the rest of the surrounding materials. It just acts as a heat sink, so it can spread out much faster when you have open areas over there. So this is how they have been doing. The professional pack companies have been doing, and they have been adding slot all over, so that you do not apply large amount of current, which would lead to large heat generation over there, when you can get the same with a small amount of current for a limited period of time with a slot in between. It's not going to affect much. So, and then we have wire bonding technique, so which is also another important technique which is coming into picture in recent days. So this wire bonding technique is something which has been widely adopted by Tesla, as you might have seen. So unlike spot welding, there is no manual process for wire bonding. It is a fully automatic line, and it has several advantages compared to spot welding. Like here, if we see this image, we could see the cell's positive tap portion is fused with aluminium string to a bus bar. That's the welding mechanism, and the current is passed through these wires bonded on both the sides. So when there are more than two wires for a cell, depending on the diameter of the cell, like for this you can see only one. If the cell is bigger and you want higher currents, or you want much more stability, instead of one wire you could put two wires or three wires, but again the diameter of the cell should be sufficient enough for you to do that. For example, 18650 cell will not be able to support the wire bonding technique because of its smaller diameter. That's the reason the wire bonding starts with 21700 cells, and that's what Tesla has been doing. So some of the advantages of this is like wire bonding. This wire bond is basically aluminium, and aluminium has better thermal and electrical conductivity compared to nickel. Since the wire bonding is aluminium, it can take high currents, and if more high current is passed through these wires, what happens is then the required current. So this wire is designed for a certain specific current, and that is how this wire bonding is done. If the cell is delivering such high current, that means if the cell is misbehaving and the cell delivers any amount of high current, the immediate thing what happens is this this wire acts as a fuse. So this being aluminum material, which is having a certain specific melting point for this area, if high current is being transferred through this, because of that high current being transferred, this wire bond immediately acts as a fuse, and it melts and it breaks itself from the other group of cells. By doing this, which means there is one cell which is misbehaving, and that cell is out of the loop, which means the whole module is safe now. You don't have to be worried that one heat from one cell is going to be translated to other cell, and in that way all the cells catch fire. So that is the common case in most of the permanent welding techniques like laser welding or spot welding. But in this one, the fuse itself, the wire itself acts as a fuse, which is a great advantage for this one. At the same time, we have aluminium. When this aluminium is the current carrying path from the cell to the bus bar, it being aluminium, it can always conduct away heat outside through radiation. So the heat is always being dissipated. So the bus bars or the fuse links are never hot when compared to what a spot welding technique would be. So these are certain advantages of having a wire bond. Like what they are, like it is a fully and fast automatic process. Links are tested automatically against strength. So you bond the wire, and the same machine would test it for its strength. So it will have a pull mechanism. It will hold the wire and pull it to see that the bond is good or not. And one more advantage over here is what happens is, if it's a spot welding, if you see here, there is a permanent joint which is formed over here, and if the bond breaks, which means you will have no other option to weld it again. Whereas in this cylindrical cell, if the bond breaks, it's very easy to service this again. You will not have to damage or throw away the whole module. You can again rework on this. You can again put a fuse, you can remove the small particles over here, and you can put another joint and use the module again. So it gives a great leverage in reusing the whole battery pack again. There is no wastage. And then being aluminum material of the wire, it has a better thermal dissipation. And then because this is aluminium and this is reducing a lot of material, which when compared to nickel, the whole weight of the pack comes down. And yes, it also has lower weld resistance when compared to any other spot welding techniques, etc. So these are the advantages of wire bonding, but the only disadvantage could be with respect to our Indian conditions, so where there are a lot of potholes, lot of uneven roads, etc. It little bit makes more complicated for using wire bond design. It has to be designed so that it is intact against the vibrations, and this is a little bit expensive. This equipment comes with a certain cost, but yes, if there are a lot of advantages which overcome this, that could be brought down as well. Now we'll understand what is the difference between wire bonding and spot welding by going through a thermal mapping of this process. Now, here we have two different areas, two different columns where we have one module. The module is the same, it's 7S16P module, but one of the thermal analysis done is with a wire bonding technique and the other one is with a spot welding technique. So by doing this, what is that we are going to understand over here? So if we see carefully, the one with the wire bonding has same number of cells, the one with the spot welding has same number of cells, and but you see a wide temperature difference between both of them. What we could see over here is, for a wire bonding, the average temperature of the whole module is 54.2, the maximum temperature is 56.5, and the gradient, that means the cell of the lowest temperature and the cell with the highest temperature will have a gradient temperature of just 4.5 degrees. So the difference is just 4.5 degrees. But whereas when we see a spot welding with nickel bus bars, the average temperature is 68.6 degrees and highest temperature is 75.9, where the gradient temperature, which is the hottest and the lowest cell temperature, is 14.7 degrees. So you just see the difference between the temperatures of this. So there's a huge difference, which means when we go with a spot welding, some of the cells will always be at higher temperature, whereas some of the cells will always be at lower temperature, which will create a great imbalance between all the cells, because the cells at higher temperature will be deteriorating faster, and whereas the cells at lower temperature will deteriorate slowly, which means the cells will lose its capacity faster and these cells will not lose its capacity faster, and that would create a great imbalance between cell, and the BMS will not be able to handle such kind of differences in terms of voltages, and eventually you will see that the pack will terminate as quickly as possible. So that is how the whole thing gets affected. Whereas when it comes to wire bonding, since we have aluminium bonds everywhere, the amount of heat which is going to be generated by all the cells will always be constant, because aluminium is constantly emitting out heat as much as possible. Instead of being a heat trap, the heats are always liberated as much as possible. So that is one major difference that you'll find for a wire bonding and a spot welding technique. Though the cost of the cells higher, but if you see the performance wise, this is something which you will be impressed with the wire bonding, because the gradient temperature is just 4.5 degrees, whereas the spot welding gradient is 14.7 degrees, which is like 3 times higher, which means the life of the wire bonding would be 3 times more better than that of a life of a spot welding module. So this is the outcome of this one. So it's important to understand both of them and choose the right spot welding or wire bonding technique. So let us now discuss on laser welding, cell to cell interconnections. So laser welding and ultrasonic welding are something which is most common for the pouch cells, and laser welding is a little bit complicated when it comes to other techniques, because laser welding requires a good clamping system where we need to clamp both the bus bar and the cell at the right place, at the right joint, so that the fusion happens correctly, or there could be wrong points where we could fuse it and the joint might not be as perfect as needed. So, and also laser welding allows welding of any material bus bar, like aluminum bus bar can be used, or a copper bus bar can be used, or a nickel bus bar, a nickel coated copper bus bar can be used. And usually copper bus bars are coated with nickel to avoid any oxidation or any such things to happen, because copper tends to oxidize when it is heated or it is fused. So these are certain safety or precautionary steps that are taken while using or choosing a correct bus bar. And now if we see the kind of materials which are used for the bus bar is usually when we have 3 different materials, copper, nickel or aluminium. We always should be choosing a material which is low weight, which has better thermal conductivity and good electrical conductivity. So in that way we could choose aluminium because its density is less when compared to copper, but even though copper has a very good electrical and thermal conductivity, the weight is something which plays a major role over here, and that is the reason we could choose bus bar which is of low weight, which has good electrical and thermal properties. So that is one of the reason where aluminium comes into picture. It plays a very strong role in most of the bus bar materials needed for cell-to-cell interconnection, especially for laser welding. So now if you see laser welding, we can see here there are 2 different ways to join the positive and the negative of the cell. So here there are two ways where we can join cell to cell directly, or we use cell to busbar to cell. So we have copper tab, which is of very thin size, and usually this is for a pouch cell, and since we are talking about a pouch cell, the tabs are very thin, and the busbar also has to be of same thickness or equal or a little bit more thickness than what it is. So when we talk on the first one, which is cell to cell, you have a probe and you can join it in a straight line. This is the joining area, which means the cell of the first one, I mean the negative or a positive of the first cell is connected to the next cell's positive or negative through a straight line. This is called the tab to tab joint. So this is the cell to cell is directly joined. You're not going to use any busbar over here. So that is one advantage that you get with the laser welding for pouch cell, because the weight that is taken by the busbar is eliminated completely. But whereas there is also another technique where you use a busbar to the cell, and then this other side of the busbar is joined to the other side of the cell. So over here also you could see a straight line. So this is one advantage of this busbar, where you can have a U joint. By doing a U joint, your tabs are always straight, and by bending the tabs you can always form heat affected zones over here, because if the bend is not right, there could be resistance built up over there. So the bending radius of the cell is also something which has to be iterated, and it has to be arrived accordingly. But whereas when you have a straight tab, you don't need to bend it. So when your bend is straight, there is no resistance or no heat affected zones forming over a straight object. So that is the advantage which you get over the cell to busbar and cell to cell combination. So there is a certain trade-off that has to be made in this kind of technique which is used. Whether you use a cell to cell, avoid the busbar weight, and take care of your bending radius appropriately, so that you can get a good joint and the functionality is served, or you take a little bit of lenience, or you can say you are safe. You wanted to play safe by using a busbar and keep the tab straight, which is a safe game, and then you weld the joint. You join the busbar to the cell tab, and the other cell tab is joined to this busbar, and still you can still work with this. So both are equally good. It's just that you need to make a good trade-off which one you want to. So now here we see a prismatic cell laser welding. And as we have seen that laser welding and ultrasonic welding are common for pouch cells, similarly laser welding is used for prismatic cells as well. And here we see three different cases for prismatic cells, where we have the first one which we would say as a good joint, the second one which we would say as a average, and the third one is a poor joint. So how do we classify it? We classify it depending on the kind of joint by looking with a naked eye initially. So if we see a naked eye, with a naked eye, we can see that the first two joints are almost same. We would feel that the first one is a joint where there's a lot of fusion happened, a lot of filler material is used, and the second joint is something where that amount of fusion has not happened, but the joint well looks good. But the third one is definitely a bad joint even with a naked eye. So if you see the first one, there is a proper contact and a proper fusion formed between the busbar and the cell tab. That we can see it over here. There is everything is red, which means the filler or the metals have been fused perfectly. When with this kind of joint, what happens is when the current passes, the current has the whole area available for it to pass through the busbar, from the cell terminal to the busbar, to the another busbar, or to the power cable. There's a lot amount of area available, so it can pass through this area and it will pass through the whole busbar, so that there is no resistance, there is no contact resistance build up over here. So this helps in maintaining low contact resistance and low temperature build up over here. Whereas when you see the next one, you can see the pockets of area which has been left vacant, which means there are certain places where the metal has not fused well. When that happens, when the current is passed through these busbars, this area of the creamish area which is left blank is something where you have voids, and the current can never pass through this, which makes the current to pass through the same area you'll have to pass more current through the less area, which increase the contact resistance of the whole operation. So you'll have to witness higher temperatures over here. You'll have to witness hot spots at these locations, and this area where it is not welded will act as a void, and it will not allow much current to pass through it. So it's always to be seen that the current has enough area to pass through. This will create a bad joint, and literally after a period of time when there is high amount of current passing through, it will damage the whole joint. So that is what going to happen over here. And then the third one is something which is a very poor joint. Even with the naked eye you can see that there are pockets of welds formed, and when the current has to pass through that, it will just the current will not even pass through this, and there will be very little bit amount of current which will pass through this, and that is going to be liberated out as heat. This is what a good average and a poor joint would look like, and I would always prefer this kind of joint rather than this and this joint. The second joint can be improved a lot so that the current has maximum area for it to transfer and without generating much amount of heat. So the next concept is ultrasonic welding for pouch cells. This is a unique concept which is only suitable for pouch cells. The reason why this is only suitable for pouch cells is the tabs of the pouch cell, as we saw earlier, they are very thin, and if we want to join one tab or to the other with a bus bar or directly, the metal to metal thickness has to be as less as possible, because there is no heat or any laser being used for this kind of process of welding. So everything over here is micro welding, and it is done through vibration by a clamping force. So the advantage of this is any two dissimilar metals also can be used for this ultrasonic welding. So this is actually a combination of four forces together, as mentioned over here. We have micro melting, we have metal interlocking, which is mainly due to plastic deformation, and we have atomic diffusion and metallic bonding. So what happens is you have an anvil which is completely stationary, and you have a workpiece over here, and you have a sonotrode which is giving sufficient clamping force, and it starts vibrating. And with that kind of vibration, there is a metal interlocking formed because of plastic deformation of both the materials, and they get fused together. So this is what we see in the next. There is a weld which is formed over here. So when we translate that to a pouch cell, here is what we can see, a clear picture of what happens over here. We have three different cells. We have three bus bars which are put together, and then we have three tabs of the cells which are in contact with the bus bar, and then we have a support or anvil which is coming over here, and we have a sonotrode which comes in contact with these tabs with the bus bars, and it starts vibrating over here. And with that kind of vibration, there would be ultrasonic this is by ultrasonic vibrations, and with that there will be metal to metal interlocking which takes place between these tabs and the bus bars, and that's how a joint would form. And one advantage, as we said, the tabs can be aluminium and this can be copper, and though both of them can be joined, but there would be a limitation in terms of thickness of these bus bars in the tabs, and also how the arrangement of this bus bar. If this is something to be done, it is easy because the tabs are facing on the top, like in the vertical direction. But if there is something that to be welded on a horizontal direction, the whole setup would be different, and it would be a little bit difficult if you want to do with a prismatic cell, because usually the bus bar thickness of the prismatic cell and all would be at least 5 mm thick or 4 mm thick and all, and the tabs which are used for pouch cells are hardly 0.25 or 0.3 mm thick. So this makes those kind of welding techniques like ultrasonic welding easy when we have thinner bus bars and thinner tab materials, which is the case for pouch cells. Now the next slide is we will concentrate on the factors for hotspots on the bus bars. Now till now we have seen and gone across different welding techniques, different cell types. What are the bus bars, how are they clamped, how are they welded together. This is the reason why we are concentrating on bus bar and cell to cell interconnections so much, because when we have a group of cells put together, a common thing which we will find out is the hotspot, and that is definitely going to be the bus bar portion. That means when there is an interconnection between the cell to cell, that is the portion where you will always find hotspot. And that hotspots, some of the major factors for that are the bus bar materials resistance, what is the conductivity of that bus bar, and the next one is the weld joint resistance and the current capability of the bus bar, and the cell tab building, which is the case for pouch cells, and wrong welding parameters. So all these are something which we have discussed in the previous slides. What could a current carrying capability do? For example, what does current carrying capability mean is you have selected a good material, like you have selected an aluminum material, but you have taken a wrong area. You have not considered the right amount of busbar width and thickness, and you have chosen the best material. That means you are pumping in more amount of current than that material is supposed to carry, and that would lead to a hotspot. That would lead to the bus bar to be hot always. So it's not just the material that plays an important role, it is also the current carrying capability, which is the dimensions of the bus bar also plays a very important role in avoiding hotspots for the bus bars, and also the resistance of the material, bus bar material, since the popular materials which we have are copper, nickel or aluminum. It also is important to weigh which material has a good thermal conductivity and the lowest electrical resistance, so that the job of carrying the current to the bus bar is done well. So these are some of the factors that we would consider for the bus bar. When we say about cell tab bending allowance, when we saw in the laser welding of cell to tab bending, when we say one cell tab is bent onto the other cell, it is very important to maintain a certain bending radius, typically like 0.2t or 0.25t or so. If that is not done, what happens is the tab which is bent for the pouch cell, there is a continuous stress that would be acting on the electrode which is inside the pouch cell. So if that bending is not done, if it is overbent, the seals of the bus bar or the seals of the pouch cell and all the enclosure material which is used, the aluminum foil externally used, will slowly start rupturing over there. So that is why the cell bending allowance is very important, to do a right joint between cell to cell joint when it's pouch cell. So now let us discuss on bus bar selection parameters. So till now we have talked about welding techniques, so we have talked about different cell form factors, how are they joined together, etc. Now let us a little bit discuss on the material matrix of the bus bar. Now over here we have considered 4 different materials. We have copper, we have aluminum, we have silver, we have nickel, and I have listed out over here electrical resistivity, thermal conductivity and density. So when we say over here, obviously we'll choose the best material, like material which has the lowest thermal resistivity, lowest electrical resistivity, and which has the best thermal conductivity. So if we choose that, if we see the best material, we'll find is silver. Definitely silver is not an option because of its cost, and silver has the lowest electrical resistivity of all 4. It has the best thermal conductivity of all 4, and the cost is high, but you need to also see the density. The density itself is also higher than all the materials. So being it a costliest metal and also the density is something which we can avoid using silver, because it's a highly cost bearing element. So then the next focus shifts on the next better material in terms of electrical resistivity, which is copper. It has the lowest electrical resistivity, like 1.68, and it has a very good thermal conductivity of 3.85, and then it has a density which is much lower than silver, but which is very much higher, like 3 to 4 times higher than that of aluminum. So copper can be an option, but the weight is something which we have to look at. So this would make a same bus bar of same dimensions 3 to 4 times more heavier than what an aluminum would do. But if we see aluminum, it has a decent electrical resistivity which is 2.65, when compared to electrical resistivity it is 1 unit more, 1 digit more than what electrical resistivity is, and thermal conductivity is approximately half of it, and the weight is 3 times less of it. So if we see in either ways, we can have a good trade-off by having aluminum material with a decent electrical resistivity and a good thermal conductivity, and also much lesser in weight. So this is how we could choose a right material. If weight is not a concern, yes, copper can be a great option because it has everything well performing parameters for copper, but aluminum is selected because this is EV. In EV, weight is very crucial. If it's having high weight, the whole pack, whole essence of making a pack itself goes down, because we cannot have a very heavy pack that itself delivering the power would not make a good vehicle at all. So you need to make sure that every component you choose has to be accounted for its weight also. So that's how aluminum can be a good material for busbar selection. Now we'll understand how do we generate, how do we understand the current carrying capability or the dimensions of the busbar. So if we go with the normal law of thermodynamics, this is something which you might have read, like heat is generated I square RT. I is the current carried, R is the material resistance, and T is the time for passing current. So material resistance is something which is dependent on the material resistivity, which is a function of area, which is a function of width, thickness, length, etc. So this is something which I would leave it to you for you to do some exercise on, where you have all the electrical resistivities of the material. You could choose any area or any bus bar of any thickness, any length and width, and depending on that you arrive at a material resistance, and then you select a current, maybe 100 amps or 200 amps, and then for how much amount of time you want to pass the current. So your material resistance is dependent on width and thickness and also length, which you want to have from one cell to another cell, which is variable. Depending on that, you will understand what is the heat generated for a bus bar. Now that is heat generated for the bus bar. Now we would also like to understand what is the heat generated in a cell. So now it is also using the same formula, which is Q is equal to I square RT, where I is the current delivered by the cell, R is the resistance of the cell, which varies at different SOC percent. This is something which we'll discuss in detail in the next slides, where resistance is not at all common for a cell at all times. So unlike busbar, where you can take a constant resistance, that is not the case with lithium ion cell. Each SOC it will have a different resistance, and then you have time for delivery, time for current delivery. Now the example which I have taken is a cell with 100 Ah, which has a resistance of 0.5 milliohms, and we are assuming a resistance for that instance of time for a particular SOC only. It is 0.5 milliohms and it delivers 100 amperes of current for 1 hour, which is at 1 C. And the total heat generated would be, we will be using the same equation, Q is equal to I square RT, and by equating that we will be getting 5 watts, and then we give it for Q is equal to mCp delta T, and we have considered the mass of this cell to be 1980 grams, and the specific heat capacity of any material is 1.35, and that you multiply with delta T, and you get a delta T of 6.7 degrees at 1 C. So you can see that there is a delta T when you discharge a cell at 100 amps for 1 hour. You can see a delta T of 6.5 degrees. These values are subjected to change, and you can take these values from any of the cell OEMs by understanding what is the weight of their cell and what is the specific energy capacity of their cell. So and then you could quickly calculate it. But this is just for theoretical calculations, but you want to have a very good picture on how the heat generated is there in the cell at different SOC, because you are going to discharge the cell from 100% to 0%. Your SOC is changing, and so is your internal resistance. So which means your current heat generation also changes with respect to cell, with respect to cell's SOC, with respect to current, and with respect to time of delivery. So this is a dynamic equation which we have to do extensive testing to understand each and every parameter of the cell. So now as I said, now the resistance of the cell varies with respect to SOC percent. We'll discuss that in detail. So now we'll understand what is the effect of SOC percent on internal resistance. This is not just the effect of SOC on internal resistance. Here we can also understand how, in the same graph, we can also understand how the resistance is built up with different C rates. And here you have assumed the operating window, saying as the best operating window, and we have on x-axis we have SOC percent, and we have internal resistance on the y-axis. So if you carefully observe, when the cell is at 0% SOC and when the cell is at 100% SOC, when it is 0 to 10% and it is 90 to 100%, the cell's resistance are quite high on both the sides. And whereas when you assume it from 10% to 90%, the SOC is almost within the same range. So this is what it shows, that this is what it shows, that why do you have a need to avoid the first 10% and the last 10% of the cell to avoid a usable SOC window. So you basically cut off the higher resistance windows which is responsible for generation of heat more than what it is from 10 to 90%. So by doing that, you are avoiding stresses on the cells. So let us discuss as per the C rate. Now let us see a cell when it is discharged at 0.3 amperes. So when you are discharging a cell at 0.3 amperes, when it's at 0% SOC, and you are trying to discharge a cell, which means, just see, for example, your cell is at 100 Ah, 100% fully charged, and you are discharging, which means it will have a resistance of 0.2. And if your SOC is almost at 0% and you are trying to discharge, your resistance is going to be point higher than that. It's going to be 0.205 or 0. Near to 0.21. So when your resistance are so high, your amount of heat generation is directly proportional to that resistance. Whereas if you chop off the first 10% and you chop off the last 10% and you operate from 10% to 90%, even though this 10% becomes your 0%, when you start off, you are at 0.19. So when that is the resistance level you are playing at, and at 90% also, you are at 0.195. So you are almost 0.1 less than what, that means 10 times less than what you are starting with. So this is how you understand that why is it so important to resist using the whole SOC window, the whole band of voltage, and use only the best operating window always. So this not only tells you the voltage cutoffs, etc. This also tells you how your resistance varies with different SOC percent. So it's very important to do a very extensive testing to understand what is the internal resistance of the cell at different SOC, and then you map the thermal heat generation of the cell and then translate that into temperature rise. That is how you have to do a thermal load calculation or thermal loop calculation from the cell testing, and then you slowly develop into a thermal loop design model, and then you choose the right material to dissipate the heat or the right cooling mechanism to dissipate the heat. And the same graph over here also shows how at different C rates your resistance builds up. Like for the same SOC window, 10% to 90%, as your C rate is going up, as you are trying to draw more power from the same cell, your resistance values are increasing accordingly. So the resistance at 10% for 0.3 is something around 0.19 or 0.1925. Whereas when you want to do at 3 amperes, now you could see that it is more than 0.205. So it is much more higher than what it is at 0.3. So this is also one factor which is leading to heat generation. So it is important to understand all these characteristics of how SOC percent is playing an important role in the effect of internal resistance. Also, how you need to avoid the first 10 and last 10% of the voltage windows, so that you don't enter into that highly stressed zone. And also you have operating temperature also, because when you have higher operating temperature, as I said, like the electrolyte which is there inside slowly gets vaporized, and once that is done, the ion movement becomes difficult. So that is also one of the reason where the internal resistance builds up because of higher operating temperature. And what is the effect of internal resistance? As we see in the previous equation, internal resistance R is directly proportional to heat generated, and current is also inversely proportional to heat generated. The more you draw current, your heat generated is increasing, and the more resistance is increasing, your heat generated is also increasing. You need to see where is your best operating window, and with that, how much is the heat being generated, and with that, how do you choose the right cooling material or a cooling design for that. Now let us enter into the thermal dissipation loop and thermal interface material considerations needed for a cell. In this topic, we'll understand how to extract the heat from the cell, like through various mediums. Till now, we have been talking on what are the causes of heat generation, how do we understand the resistance, SOC, and how do we mitigate that and lower the heat generation. Now we'll be concentrating on how to dissipate the heat and how do we design that. So here we'll understand some of the thermal materials which are used in cell or a pack or an enclosure, etc. So if we see over here, there is a small schematic which we have earlier we have seen a cell, thermal material and a pad. Similar is the condition if we want to use for a cell. So this is the thermal pad or a thermal interface material. So what does it do? Because when we are going to have a cell to cell or a cell to heat sink contact, there are a lot of air gaps that would be formed which acts as insulators. So that is something which has to be avoided as much as possible, so that there is a seamless thermal conducting medium from the cell to the heat sink or an enclosure or any other source which dissipates the heat. So this is what happens. The cell generates heat. It is passed to the enclosure, which could be aluminium, through a thermal interface material. And that thermal interface material is something not new. It has been in existence from many years. And it is available in different forms. It is available in thermal pads, it is available in thermal foams or thermal paste. But what is the science behind it is the selection of the right material and thermal conductivity is something which is very important, and that is something which we'll have to do it over a period of time by understanding the cell heat generation and the temperature reached. So when we talk about the schematic diagram again, we can see that there is a cell and we have a thermal pad in between enclosure. And enclosure, when I said it has to be aluminium, because aluminium has good thermal conductivity. Whereas if we are using a thermal pad and a cell and we are using a MS enclosure, and that MS enclosure is usually powder coated, and MS enclosure, mild steel, is a very bad conductor of heat. It doesn't conduct anything at all. So it doesn't even make sense if we use and we have a cell and then we are using MS enclosure. It's waste of effort. So a proper right combination has to be made always when we are putting different materials together. So if we are using a thermal pad, it has to be made sure that the enclosure being used also has a very good conductivity, or the essence of using a thermal pad is completely lost. So that is something one of the important consideration when it comes to thermal dissipation considerations. So the next slide is thermal interface material conditions, where I would just like to say that TIM is thermal interface materials, and I would be calling it as TIM just to cut short. The thermal conductivity of TIM is something which is very important. So the TIM is being in use from many applications, like it is being used in power electronics like MOSFETs mainly to dissipate heat because they generate a lot of heat. So hence the application, their use remains the same, but the thermal look and its design and its application differ. So some of the considerations needed are like the thermal conductivity of the material should be as high as 5 watt per meter Kelvin, but that comes for a price. So it is important to have a good trade-off between the cost, its application and the performance also. So it has to be selected properly, and we need to understand the maximum temperature rise that happens in the cell, and then we select the thermal conductivity of the material equally. It doesn't make sense like we choose a very high thermal conductivity material when the heat generation is very low. So it is that, like, it is very important is the area of application. So just to give some heads up, like it is recommended to go through week 1 session where you could understand where we have all the thermal pads written. Like you could refer the module design for the pouch cell, module design for the prismatic cell, where we see a lot of thermal interface materials placed on metal plates placed over there. So over here, just to refer that, some of the area of applications of thermal interface materials are within a battery module. We have a cell and a heat carrier plate which is applicable for pouch cell, and then we can have the same thermal interface material between cell and then external enclosure. And then we have types of form factors, so different cell form factors and application. So it differs from the types of form factor and application. For example, if it's a cylindrical cell, you cannot use it across the body, but you could across any one side of this one. So but application is like where are you going to use it and how much of the heat is going to be generated there. And then also you need to consider the set of compression forces that are required for assembly. For example, if you are going to use a thermal interface material of foam and you are going to use it for pouch cells, you need to understand what is the compression force required to compress it so that it is of actual right use to you, to avoid expansion and contraction of the cells. Then the most important part is, are you going to use a thermal interface pad or a foam, so that when you have set of cells over here and you are going to slide all these cells into the module, how easy the assembly is going to be. And that is something which is to be evaluated. So whether you're going to use pad or a foam or a paste, and how easy the assembling sequence is going to be, that is something which you have to look at. So there are multiple considerations for a thermal interface materials to be selected on. It doesn't happen over a period of time. You need to evaluate a lot of conditions for that and then arrive at the right thermal interface material. And then what is the thermal design loop for a pouch cell? So I would suggest you to refer the week 1 session again, just to have an idea on the thermal interface on the module design concept over here. Or the process of thermal design loop for the pouch cell is like this. This has the pouch cell come in different form factors, and each cell has a different form factor. When I say form factor, it is in the terms of dimension, and the enclosure design is completely different. So therefore the thermal loop sequence has to follow in this way, that when there is a compression foam, it has to accommodate the expansion and contraction of the cells. So that means you have a cell which is 1 mm thick, and you would compress it only up to 70%. That means it becomes 0.7 mm, and you put that between the foam, between the cell and the HCP, so that when your cell is expanding, that 0.7% is reduced to 0.2 or 0.3 or 0.4, and whenever the cell is contracting, that 0.7 mm increases to 0.8, 0.9 or 1 mm. So you don't have any space left vacant whenever there is an expansion or contraction going on during charging and discharging. That is something which is very important for a thermal loop design of a pouch cell in selecting the right foam. And then this conducting foam should be having good conductivity. It should have a good electrical resistivity because there is a HCP which is a metal and it is in contact with that. So you should have a good electrical resistivity and also good conductivity. And the next point is the same. HCP, as it is in contact with the cell, the enclosure, or is in contact with the HCP, through there you put a tin there, so that the cell is in contact with the HCP through a thermal foam which conducts all the heat to the HCP, and HCP is conducting all the heat to the enclosure through a TIM. That could be either a foam or a paste or a pad. So that is how you design a thermal loop for a pouch cell. So though, yeah, it was complicated because it's a pouch cell. The thickness is not favorable for us. As I said, pouch cell designs are always complicated. But that is the only way we have to extract as much as heat as possible. This is a pictorial representation of how we can have it. So over here, this is a plate, HCP. And then we have a tube over here. We have a pouch cell. This is a liquid cooled plate. So just to make this whole heat extraction even more effective, we can use a liquid cooling for each cell. So these are the inlet and outlet pipes. Over here is the place where you can put a thermal pad. So that is what we can see over here. So you have a pouch cell and you have a compression foam over here, and you put a HCP on the top of it, and you have several blocks out of that, whereas this HCP or this cell blocks are in contact with the thermal pad with the enclosure. And remember, this enclosure should be a material which is conducting away heat, not a material which is very bad conductor of heat. So you have cell blocks which are in contact with the enclosure through a thermal pad, and you have a pouch cell which is in contact with the HCP using a thermal foam. So your loop is completed. So that is how you need to design everywhere, that you transfer as much as heat from the cell to the enclosure, so that at the enclosure level you either have air going through and the heat is taken away from there. So this is for passive. Whereas if it is active, you can see over here, like you have inlet and outlet collector tubes, and you have water directly running through these channels, and the heat can be extracted away like that. And since these are pouch cells, you can use thermal pads over here, and that gives no air gaps between the cell and the heat carrier plate, and in that way the dissipation is much more better. So the next one is the thermal loop design for prismatic cell. Here we would be at a relief, because now we see the prismatic cells, as we discussed earlier. The prismatic cells have certain thickness which makes the whole concept of thermal dissipation very easy. Since we have wider thicknesses, wider areas, everywhere we could put thermal pads directly, And we don't need a complex thermal loop there. Like unlike in a pouch cell, we have a pouch cell, we have a foam, we have a heat carrier plate, and then we have a thermal pad, and then we have an enclosure. Oh, this is really tedious and very complex operation. Whereas in prismatic cell, it becomes very easy. You have surfaces directly over here. You can put thermal pad over here and fix an enclosure on top of that and extract heat. It is as simple as that. So this is the main reason why prismatic cells with higher capacity are always used. It also makes the whole design loop very easy when compared to pouch. So here is a little bit more information on thermal loop design for prismatic cells. So this is a prismatic cell typically used. Let us understand like the base enclosure. We have aluminum and we have two prismatic cells. And if we see over here, we have very wide thickness for the prismatic cells on both the sides. Like we have area at the bottom. So if seen properly, we have a lot of advantage by using thermal pads on all the three sides, and see that we can extract heat from the side and the bottom as well. So this is one major advantage that we'll have with the prismatic cell compared to pouch cell, that the design loop becomes very easy. There is no much contacts needed, no essential need of one-to-one proper contact always, because as many contacts come into picture, we also have the same resistance add up. There will be a lot of air gaps which will form. The whole process becomes complicated. But over here, we just have a cell. We can put a thermal pad on the side. We can put a thermal pad at the bottom, and we have thermal heat sinks, or good thermal conductive heat sinks on the side and the bottom, and the heat generated by the prismatic module is taken away as easy as. So this is one advantage of using prismatic cells like this, unlike pouch cells, which has huge complexity when it's compared with pouch cells. Also, we have direct cell contacts over here, so we don't need to use any HCP over here. We can have a direct contact with the cell. So that is the greatest advantage over here. And now since we have discussed on all these topics of thermal dissipation, thermal loop designs, etc., let us get into a little bit of ingress protection type and what its needs. So ingress protection is something which is dealt with entrant of water or any entrant of dust particles into the battery pack, and that can cause a huge damage to the whole battery pack because there are a lot of electronics sitting inside it. There are a lot of metal objects inside it. The busbar mainly are all conducting materials, and we have cells which are highly conducting material. And if there is any small particle or any metal piece which goes and sits on any of the busbar in contact with any of the other busbar, it's going to lead to short circuit, etc. So that's the main reason why we need to have a very good ingress protection. It's not just that, like if you keep allowing the dust to be accumulated on the busbars, now we have put a serious effort on understanding how important is it for the busbar to have thermal conductivity so that the heat generated through it is always dissipated. Now imagine if that is accumulated by the dust, it's not going to be as effective as it. So those are some things which is really driving the need for ingress protection, and let us go through it, what it says in the next slide. So what is the need for ingress protection? So the most important part for ingress protection is, now the whole IP has been classified into different levels. The whole IP is called ingress protection, and it plays a very important role in the battery pack performance. Like what happens if we have a very bad ingress design? It will allow entry of solid and liquid particles into the battery pack, and when water enters into the battery pack, it can cause a lot of havoc. Like the metal components which are there, like the bus bars or the screws which are used for mounting the cells, or the bus bars, or the BMS, or for tightening the enclosure, etc., everything gets rusted. And if such thing happens, then the whole resistance of the whole pack goes up. It would lead to a bad performance of the whole battery pack. So ingress protection is something which has to be designed properly, and it has to be taken care very seriously. So water ingress is something which can lead to rusting of the battery pack, and the bus bars in contact with that also gets affected because of that, and it can also cause electrical failures. It can cause short circuit, because water being one of the major culprit in terms of all short circuits, etc. And there could be a lot of wires with current running through them, and water coming in contact with that can create a havoc. Same is the case with solid ingress protection. So when we have a break in the ingress protection, solid ingress can be anything. It could be dust, it could be metals, it could be solid particles. And when such thing happens, as I told earlier, like dust is accumulated on the bus bar, and when that happens, the bus bar's major design tendency of liberating or dissipating heat as much as possible when the current is passed is lost, because the dust is formed on the cells and that actually covers the whole bus bar, and it doesn't allow the heat to escape, and it becomes heat trapped there, which eventually leads to overheating of the bus bar over a period of time. And because of that, the whole efficiency of the battery pack goes down because of that. So that is the reason why we need to have a very good ingress protection need. So let us start into the first level of IP protection level, which is IP dash or -X. So when I say solid ingress is mostly related to the first digit of the IP protection level. Usually IPXX is the term which is used, where the first digit is for the solid protection, and the second digit is for the fluid or the liquid protection. So the first one, when I say IP1X, which is the basic one, and IP6X being the highest one. With IP1X, it is to be that there has to be a protection against any solid object which is having anything dia more than 50 mm, like hand. And then if it is IP2X, it should have a protection against those solid objects which is having anything of size greater than 12.5 mm, which is a finger. When it is IP3X, the protection has to be against any object which is having a dia more than 2.5 mm, which could be a screwdriver or any nail or any sharp object, etc. And then IP4X is something where you need to have a protection against a solid object with more than 1 mm dia, which could be wire or any other thing which is like 1 mm. And then IP5X is something against dust protection or limited ingress. So there will be no interference with any of the operating equipment. So this is something which is a little bit higher than 4X. So it is only limited to dust protection. And IP6X is seal tight. So you would not have any particle or any dust particle or anything entering into the battery pack if it is IP6X. So usually the best recommended is IP6 for a solid ingress protection, and similarly we would see what does it take for a liquid ingress protection levels. So in liquid ingress protection levels are again, so as I said earlier, it is IP-X, and in this one IPX- is the next. So the next level of protection, which is liquid ingress protection, that is IPX- or X-. So the second digit is something which is related to the liquid ingress protections. So here this is something which we will deal against protection against liquids. The first one is something which we will deal with the protection against solid objects. So when we go with IPX1, we'll have to see that there is a protection against vertical falling drops at a rate of 1 mm per minute for 10 minutes. And then if it is X2, we'll have a little bit more complicated situation we're creating, where we'll have to have a protection against diagonally falling drops up to 15 degrees, and that is also for a rate of 3 mm per minute for 10 minutes. Then IPX3 is little bit more higher. So this is the intention, like when we go on increasing like level IPX1, X2, X3 or IP1, X2, X3X, the intensity of protection against ingress increases. So the higher the level we are, the better the protection we have against ingress. Similarly is the case with IPX3, where we are going to spray a water for 5 minutes at 0.7 liters per minute at a pressure of 80 to 100 kilopascal. And then we have IPX4, where we will be splashing water in all the directions for 5 minutes at a speed of 10 liters per minute for the same pressure, 80 to 100 kilopascal. So here is the directions or images which we can see. First we start with small drops on flat, then we go with inclination, then we have water spray coming in, and second IPX4 is for all directions, and then IPX5 over here. Here the whole flow rate, etc., everything gets increased now. Now we are going with a water nozzle instead of a spray for 3 minutes for 12.5. Earlier it was just 10 liters per minute. Now we have increased to 12.5 liters per minute, where the pressure is 30 kilopascal, right, from a distance of 3 meters. And then IPX6 is even more higher, like We are going to have a protection against 12.5 meters water nozzle for 3 minutes when the flow rate is 100 liters per minute at 30 kilopascal for the distance of 3 meters. And IPX7 is it's not even more complicated. From here again, we come into a functional point of view. So when it is IPX5 or X6, we are looking at it an angle when someone is throwing water onto the body or battery pack. So here we are going to pressurize water onto the battery pack. But when it comes to X7, the functionality changes. Here we are trying to submerge the battery pack into the water and see whether water is entering into it. So here is another type of design sealing that has to be done. So both are different in their own ways. Over here, when it comes to X5 and X6, people tend to say, oh, it is X7, it is much more good than what it is X5. No, that is not the case. The functionality of this seal ingress design is different. And same is the case for X8. Here we are looking for the ingress against water depths up to 3 meters. So we are going to put the battery pack for longer period, and the depth of that immersion would be more than 3 meters. So that is for IPX8. Now if you see, there is a slide on we'll understand what are the different types of serviceable battery packs in the sealing. So usually sealings are to be classified into permanent sealings and serviceable sealings. So when we say about different types of sealing, we have different types of process involved for sealing, which could be a silicon die cut gasket, which we can see over here. It's a seamless die cut. We use a gasket, and we can have a die of the required shape, and we can die cut it. Then we have foam in place gaskets, which is this. So there is a material, liquidified silicon, which has been melted, and it is injected through this robo arm, and it can take any profile which is needed. It is guided through a robot. We need to program the profile of that, and it is injected through the profile wherever it is needed. But it's just that it takes some time for solidification. But this is something the latest being used in most of the applications, foam in place gaskets. And then we have O-rings, which are the most common ones. So where do we use the serviceable battery pack sealings? Are somewhere where these components are more prone to opening, and again it has to be reworked and again closed back. It is not something which has to be permanently sealed. So battery pack has a lot of places where components can fail and they have to be replaced quite often. Like there could be a BMS burnt up, or some fuse is broken, or some wire is broken. So that means there are a lot of places where the battery pack has to be opened, has to be repaired, and it has to be again put back together. So that is the place where serviceable gaskets are being used, which is like battery pack over here. So that is the place where we need to use serviceable gasket, which is over here. Similarly, since there are a lot of electronic components being in place for a battery pack, like we have BMS, we have fuses, we have telematic boards, etc., there will be a lot of EMI and EMC radiations interferences happening. So that means we need to also have certain gaskets which are already available with some metallic composition with the silicon materials, so that all these radiations and interferences are stopped by these gaskets. So we can also see that we use certain gaskets with EMI and EMC shielding capabilities, so that the frequencies and there are no noise disturbances that would occur when such radiations are passed through. The BMS is not getting affected, or the telematics are not getting affected, because there are a lot of errors that this EMI and EMC can cause in a battery pack. So that also becomes a most important aspect when we choose the right gasket design. If there are such problems, if we are identifying it, it is important to choose those gaskets which can solve EMI, EMC problems also. Some of the most important design considerations for gasket are this: gasket design must be in such a way that it should not allow ingress at all for any of the objects, be it solid or liquid. So when that happens, the whole essence of using a gasket or a sealing goes. For example, let us consider this holes of this plate which are there, and we have a gasket which is the red portion over here. So when we have a hole on all the four corners, it has to be made sure that the gasket area is inside, not outside. So if these holes are inside the gasket area, which means when the water is in contact with this hole, there are many chances that water could enter through this hole. So what is the use of having a gasket? There is no need of having a gasket at all when you have a hole inside the gasket. So the whole essence of using it is lost. Whereas if you have the holes outside the gasket area, it makes sure that even if water is coming in contact, your gasket is designed in such a way that all the electronics and other components are lying inside this area, so that even the water comes, it can come and touch your gasket and it is not entering inside it. So this is how you design you take care in designing some of your gasket design. And one of the most important part is the offset between the gasket and the gasket cover. So you need to maintain proper offset between the gasket and its cover, so that when you apply proper torque and when you tighten the gasket enough, the gasket doesn't ooze out when you are applying more pressure to it. And it has to be seen that your gasket is well within the boundaries of the outer cover, and that is something which you have to take care of. And also the gasket has to be tightened, this cover with the other cover has to be tightened by using screws and nuts and bolts, etc. And when they're doing that, you need to see that a proper torque value is applied, or else if you over tighten the whole enclosure with the cover, there are high chances that you might tear open the gasket and it could lead to ingress leakage inside the cover. So this gasket design considerations are a combination of torque, are a combination of placement of the gaskets. It's a combination of how much force you apply and how much you compress the gasket, how do you place the gasket to avoid ingress protection. So it's a combination of all, and how do you assemble becomes even more challenging. You could have a great gasket, you could have a great material, but if you don't assemble it in the right way, you would always lose the gasket's importance over there. And the last important point is the gasket must be seamless, and the joint, the screw and the nut which is used for assembling two plates together, which is responsible for having a sealing, should be strong enough that they don't move away due to vibrations and other shocks, so that the ingress is still intact. So these are some of the design considerations that are needed for a gasket design. So now we'll talk about permanent sealings in a battery pack. So what are the permanent sealings? Like some of the permanent sealings which we always know are welding, riveting, or any other technique, or spot welding, or different types of joints are there which are permanently sealed. But certain permanent sealings cannot be used in battery pack, and certain permanent sealings can always be used in battery pack. So what are those? One of the most important application in a battery pack is the cold plate. So this cold plate houses of cooling tubes, it houses of running water channels through them, and its main importance is it has to hold also the modules together. So this makes it very neat that the cooling tubes, for example, there are copper tubes over here and they are assembled into it, and it has to be a permanent joint. It cannot be a disassembled joint, or if it's a disassembly, or if this joint can be serviceable, which would mean that there could be all these pipes coming out often because of vibrations and all. So to arrest that, it has to be a permanent joint. So there are certain applications in battery pack like cold plates which has to be a permanent sealing, and this has to be leak proof, or else if they are not joined properly, if gaskets or such type of sealings are used, there are high chances that the water, the coolant fluid which is flowing through these cooling plates can come out because of one vibration or one high load jerk. It could open up the whole sealing, and that could damage the whole cells, modules which are inside it. It could cause a catastrophic effect on the whole battery pack. So that is the main reason why we need to have a permanent sealing for these cold plates, so that we have one inlet, one outlet. Just there are two hoses for the inlets and outlets, and those are also sealed. It's just that the water entry pipes, hoses are fixed to that. So everything in a cooling plate is joined. It has to be seamlessly joined, and it also has to be tested against ingress. It has to be tested against air leaks or water leaks as to the best extent as possible, so that there is no leak when it is assembled on the battery pack. And it's not just a cooling plate. It also must be able to withstand the vibrations. It must be able to take the load of the modules on, because they lie on this cooling plate plate, and cooling plate acts as a base and the important structural member to hold all these modules in the high voltage battery pack. So this is where we use a permanent sealing. So yes, in short, we have come to the last summary slide where we will, I hope this would be very useful to you, where we have discussed a lot on thermal behavior of the cell, what is the internal heat generation, what are the different welding techniques used, what are different welding principles we have, what are the thermal loop designs for cell, a module, and how do we calculate the internal heat generation in a cell and a bus bar, what are the types of materials that we could evaluate for the welding of bus bar, and how do we choose the right form factor and the dimension of the bus bar so that the heat generation in the bus bar is as low as possible. We have also discussed on the internal resistance and its effect, how it's affected with respect to SOC. We have discussed on the different types of ingress protections, which is solid particulate and also the liquid particulate matter. And then we have discussed on the different types of gaskets, what are the different types of sealings that are used in the bus bar and how each sealing has its own importance. So in short, this is the summary of what we have done in this session. I hope this has been a useful session for you, and I would like to thank everyone in the image credits with whose help we were able to understand the phenomena and the science behind each and everything in a better way.